All right, this is our last section, right? Because next class is a review, and then we have an exam, and then we review for the... Now, in that review, we're going to review for the final and the last exam, right? So if you can bring all your old tests on that review day, that'd be great, because that's how the final exam is going to be taken. Take it from all the old exams. All right, so on that review, yeah, they'll be very similar. So on that review day, make sure you bring all your old exams.
Are we going to have a review like Friday before the final?
We can talk about that on review day. All right, we'll get closer.
What day is our final?
We'll talk about that in review day. I'll look it all up. It depends on what section you're in. So. And I'll give you the option of taking it in either section, because it's the same pretty much. We'll work it out. You'll come and see me. Now, okay, nuclear chemistry. Oh, Kelly. Look at this guy. You got a PhD in nuclear chemistry, Kelly did, and the question is, how's your research on nuclear waste disposal going? Have they solved this yet? Can you still get PhDs in this stuff? Right? Have they solved this problem? No, not at all. Not even close. Right? What is the problem? Well, I took this from my favorite movie, known to mankind, The Good, the Bad, and the Ugly. It stars the best actor known to man. Who is that? Clint Eastwood. All right? You want to see a good cowboy flick, that's it. Anyway, the good thing about nuclear power. Ooh, it's not supposed to give you any what gas? It gives you a greenhouse effect. Carbon dioxide. Okay, well, if it doesn't give you any carbon dioxide, Jasmine, look at this picture. What's all this white stuff coming out of there? Milk. What is it? Is that smoke? It's a nuclear power plant, by the way, and that's just a picture of it. It's water vapor. It's water vapor. Who cares, right? Water vapor. Clouds. Water vapor. Clouds are coming out of it. So it's nice, clean power. The bad? Oh, you have all this waste left over, right? And what do you do with it? That's the ugly. They have no idea. This stuff is just sitting around these nuclear power plants right now, because what state won't take it, even though we spent billions of dollars on it? Right? There's these huge, huge tunnels, and that's the idea. Just store this stuff, right? I wouldn't want to live in that state either, but it's so, I don't know. They don't know what to do with this stuff, and it's just not going to work, right? So just, I don't want to go harping on this too much, but I think scientists don't really want to say it, because there's funding, and you get money to do biodiesel research. You get money to do nuclear chemistry, but there's really only one solution to our power problems. Does anybody know what it is? No. You go out into that parking lot, right, that you parked your car in. There's enough energy from what? The sun striking that to power pretty much, I'd say 10 square miles around here. Everything. That's how much power is coming from the sun. That's where your energy is going to come from. And that's just it. I mean, that's where it's going to come from. And they can talk about all the other stuff they want. We just don't have the resources to do biodiesel. We don't have the resources to do nuclear chemistry. Okay. But that's what you'll see in your lifetime. I would bet you $100. Okay. So anyway, we're talking about radioactivity, because this is a problem, and you are living with it, right? We don't have any nuclear power plants around here, thank goodness. But I think we're talking about nuclear power. Since we're talking about power plants, they just, in Texas, if you watch the news, somebody just built a what plant right next to apartment buildings and residential areas. And it blew up in West Texas. A fertilizer plant. And I'm just seeing the pictures. There's this big black area, right? But right across the street from the plant are apartment buildings and things. I thought that was really weird. Anyway, I guess the same argument could go for the nuclear chemistry, but not really, because these guys, there's so many safety conditions that it's really not that bad. The problem is just what do you do with the waste? I mean, they're extremely safe. Well, remember though, safe meaning for the United States, because the United States has all these. If there's a meltdown, there's a huge depth of sand and concrete around these things. They plan on it. That's why they're so expensive to build, because they build in all these safety features. So United States meltdown, fine. Yeah, but we don't know. So anyway, radioactivity. Let's see, the guys in Made in USA. You get this nice orange color, right? Got some tea, but you get that nice orange color that I guess women really like. That's what it says on the internet. What's so fancy about this? Something's to about it. Anyway, to get that nice deep orange color, they use the compound uranium. Now, just to let you know what's going to head up here, these atomic numbers, the blue numbers represent, they're called atomic numbers. They're the number of what? In the nucleus of every single atom of that element. Number of, starts with a P, protons. So any atom that has more than 83 protons, where's the guy with 83? Bi. He's bismuth, right? It'll kill you in the right dosage because they're all radioactive. So uranium is way, I saw it, now I can't find it. It's like 90 or something. No, it's not 90. Where's U? Anybody see U?
Oh, 92 on the bottom row.
Oh, there it is, 92. So definitely radioactive. So, how can you tell? I wouldn't want to drink the stuff. In fact, after I leave, I'm going to wash my hands with all this stuff. But this little box. Oh, I didn't put it on so you can hear it. What is this box? Geiger counter, right? Detects radioactive particles, right? All right. Lucky, right? Here's a test, right? Put it on my hand, rub it. Hey, maybe I don't have to wash my hands. Oh, yeah, I better wash my hands. Right? Okay, so Superman is what? DC Comics? Right? Superman. What killed him? Kryptonite, right? All he needs to do is block radioactivity, block the radiation coming from kryptonite. Could he have used quiz paper? What do you think? No? Ain't gonna work. How about more quiz paper? No. How about some aluminum foil? Right? He could wrap himself in this and still walk around. No. Hey, come on, Superman people. Nobody reads comics anymore. What did he use? He went to his scientist friend, and his scientist friend made him a suit of this. Because he's Superman, it doesn't matter how heavy the dang suit is. Oh, you can't hear it. I don't want to touch it because it's lead, right? Lead is make you sick, but I'm already touching radioactive stuff. But it's in a suit. Wrapping them right inside a suit fabric. You won't touch it, right? Let's see if that works. Right? So lead works. Lead works. So that's why Superman had his suit in lead. And plus lead bends and won't break on him. It was a pretty good idea. Okay. So, nuclide symbol. No. What's his name killed him? Darkseid. Nuclide symbol. We have the element symbol. Right? Just like C for carbon. Right? Element symbol. Atomic number, we said that was the number of protons. So that's going to be a little subscript. Superscript will be mass number. Now, what is mass number, Crystal? If atomic number is the number of protons, what's mass number? Number of, anybody know? Protons and, not electrons, neutrons in the nucleus, right? Not only do you have protons in the nucleus, you have neutrons. So it's mass numbers and protons and neutrons in the nucleus. Write the nuclide symbol for a carbon-13 nuclide. You may have heard that before. That was carbon-14. They do carbon-14 dating, right, Marcus? But the carbon-13 nuclide. How would you write its symbol? What would you write? So we want to follow this convention. Someone's giving you some help here, Marcus. They said a C. What about the superscript and the subscript? Okay. Not the 12, though. Oh, sorry. Where is he? We're doing. See, he said 12. That's molar mass. 6 is going to be the. 6 will be at the bottom of it. 6 is the atomic number, right? Well, how do you know how many neutrons there's going to be? What do you put up at the superscript? You have to memorize these things? Yeah, it's a 13. They tell you. They have to, right? It could be 14. It could be 12. You don't know how many neutrons are in that isotope. Remember the isotope talk? Right? Carbon, we have a molar mass of, what, 12.0107 grams per mole. Well, if you get how many atoms of carbon? Avogadro's number. 6.022 times 10 to the 23rd. Are all of those atoms identical? No. Some are a little bit heavier, some are a little bit lighter, but they all have how many protons? 6. They all have 6. So the number of neutrons can vary, and those are the isotopes. So here's one isotope, carbon-13. Radioactive particle names and formulas. Now, the reason why we have to know this is because we're going to talk about some reactions and how radioactivity occurs. Right? What are the radioactive particles? Here's a bunch right here. We can also do nuclear chemistry and slam these little particles into atoms and create other stuff. Okay? So helium-4 nuclide. Okay? Oh, well, I'll give you this one. I'll get you started. Helium-4 nuclide. I'm missing the subscript, though. What should I write in there, Christina, for the little subscript for the helium-4 nuclide? I should put a what? It's in the far upper right. A 2. Okay, that's the helium-4 nuclide. They'll be involved in a lot of radioactive reactions. And the book's description, I don't know. They call it an electron. There's nothing really different here. I guess you could call it an isotope of helium. Okay. But an electron, we need the symbol for an electron. Does anybody know? They're going to use a little e. How about the superscript and the subscript? Ooh, 0 and -1. Good. We just have to know them. Very high energy light. They're going to call this gamma rays. Okay, or gamma radiation. How about the symbol? It's that funky thing. All right? I think that's the gamma symbol. I'm not very good at drawing this Latin stuff. So if you want to see what it actually looks like, you have to Google it. Google gamma symbol. It'll look something like this, but more symmetric, right? And the superscript and subscripts are important, though. We need to know what those are. Positively charged electrons, they exist. Book calls it a positron. Okay. So instead of E0 -1, you can have an E0 +1. You can write a positive if you'd like, but neutron. Okay, there's something wrong with doing 0, 0, though. Because a neutron, remember the mass number? He's neutrons plus protons. So the superscript isn't going to be a 0. It'll be a 1. Okay. So definitely know those names and formulas. The reason why is so we can describe these nuclear reactions. And the trick to doing it is just this. The sum of the subscripts and superscripts must be the same on both sides. That's the trick. Okay? So if that's the trick, what does the superscript, Gloriana, have to be here? That superscript has to be what? Has to be 18. The subscript has to be what, Jacqueline? Has to be 8. Yeah, because 8 plus 1 would give us a 9. Okay. So if the superscript is 18, subscript is 8, Monica, what is the symbol going to be? What has 8 protons? O. That's what you said in the first place. Right? O. Oh. Okay. That's your answer. That's the game we're going to be playing. Okay, make sense? Now, let's start way down here on this belt of stability. We said, or at least I told you, I don't know if you remember this, but Naya, no atom with more than how many protons can be stable? Do you remember what number I said? Now, if you don't remember, you can kind of look at this belt of stability. All these guys that are in red, I should have red, right, instead of black. All these guys that are in red, these dots, that's what's stable. The highest number is around, how would you drop that down? It's around 80. Yeah, it's around 85, but 83 is the number I said. 83. So anything more than 83 protons in it, it's going to be unstable. It's going to be radioactive. Okay. So let's start up on the top here. A nucleus, I'll maybe take a closer look first at this plot. We have number of neutrons in the nucleus, and then we have number of protons in the nucleus. If the number of protons equals the number of electrons, that's n equals z. You're just riding along that line. But it looks like the more massive things get, the more protons, then what? The more what you need to make it stable. The more neutrons you need to make it stable. Only this really small stuff. Oh, 20 protons, 20 neutrons, right? They're kind of the same. But once you get up higher, that belt of stability, I mean, you need more neutrons. So let's see if we can answer some questions here. Marlena, a nucleus is radioactive or stable. Just depends on the ratio of protons to neutrons. Yeah? That's all that matters in the nucleus. Nuclear chemistry, nuclear radioactivity, all has to do with the nucleus. So all we care about is the nucleus. And Helka, a nucleus with 20 protons requires about how many neutrons? Yeah, she's just looking at the plot. But 80 protons requires, Desiree, about how much to be stable? Eighty protons requires around, so if you say 80, you're talking about this, right? And don't go by the red line. You have to go by the belt of stability, these red dots. If you have 80 protons, you're going to need, I'd say around 120, right? Because you go up, follow 80, going all the way up, you're somewhere around here, right? Well, it crosses right there. That'd be 120. Somewhere around there. Okay, that's how we read the belt of stability. Some common nuclear decay reactions. Okay. Now, the reason why I'm showing you this is because you have to write them. They're going to say something undergoes alpha emission. Some isotope undergoes beta emission, positron emission, gamma emission, electron capture. That's all they tell you, word-wise. So you have to figure out, how am I going to write the reaction? Now, there's some strong hints. If it says emission, right, notice that alpha particle, right, he's on the product side. Every time it says emission, that particle is on the product side. It says what? Oh, that particle has to be on the reactant side. Capture. Just remember that. Capture means that little particle is going to be on the reactant side. Emission, oh, the particle has to be on the product side. If you remember that, and you remember what these guys are in the first place, you'll be fine. Right? Okay. Let's clean this up. Fill in the blanks for each decay reaction above if, how would we pronounce that isotope? Jalen, how would you pronounce that isotope? Right here. How would you pronounce this? CO is cobalt. So you would say what? Well, how did we pronounce? Where did we lose them? Here, carbon 13. That's carbon 13. This would just be cobalt 60. Cobalt 60 is how you'd pronounce this. So fill in the blanks for each decay reaction above if cobalt 60 undergoes that type of decay. So I better put cobalt 60 where, Ashley, in this first one? All right. It has to undergo that type of decay. It has to undergo alpha emission. So if you put it over here, right, he's not undergoing that emission. Right? If he has to undergo that emission, he has, right? This is where he is. Right? If this isotope is undergoing anything, he's always the reactant. He's undergoing it. So he's the one that's instigating the whole thing. All right? That's the radioactive particle in the first place. So it's the particle that's involved. Always going to be the reactant. Okay? If you want to put on the product side, they're going to have to say produced cobalt 60. Otherwise, it won't be there. Does that make sense? So go ahead and put cobalt 60 all along there on the reactant side. Figure out what's going to be on the product side. We're not sure what's going on here. Yeah, this looks good. Is this guy, he's 25, manganese is 25? So it has to be 28, because 28 and a negative 1 would be 27. No, these subscripts have to add up to be those subscripts. These, right? Did you see that? So you'd have to have, this has to be a 25 down here, because 25 and 2 is 27. Superscript has to be 56, because 56 and 4 is 60. Hmm? We'll go through them all. I just want to make sure you got time to do them. Well, we'll find out pretty quick. Let's ask you first. Brad, what'd you get for the very first one as your answer?
Did I get cobalt 56?
You said cobalt 56. And what'd you write as a subscript? 25. Okay. Do his subscripts, are they the same on both sides? 25 and 2 is 27. Are his superscripts the same on both sides? 56 and 4 is 60. He only screwed up one place. Yeah. What has 25 protons? I hear Mn does. Manganese. All right. That's the only spot you messed up. Okay. How about the beta emission reaction? Bianca, what did you write for that one as your answer? What did you put as your superscript? Your subscript and stuff. 60 and 28. And then you said the L-N-A. What? L-I? N-I, she's saying. She says nickel. Do you agree? 28 and negative 1 is 27. And 28 is nickel, I guess, right? How about the positron emission, Jesus? What did you say for that one? 60. Oh, you know what? We should give it the right name. Name the name. Give me the name of your answer. Iron 60. He says iron 60, right? Then I know what to write. Fe, and I put a 60 up there. And I gotta look up and see what iron is, right? Which is 26. Does everybody agree? Looks good. How about gamma emission? Israel. And name it the right way you're supposed to name your answer here. Cobalt 60. Good. Just lost some energy is all. The last one. Kelly. What did she say? Nickel 60. Okay. That means the subscript has to be, what is that? 26? 28. It has, the subscript has to be what? What's the sum of the subscripts over here? 27 and a negative 1 is 26. So does nickel have 26? What has 26 protons? It's iron? Iron. It should be iron 60. Iron 60. Okay? You comfortable with this stuff?
No, how did electron cancel?
Right? Just add the negative 1 and the 27, and you'll get 26.
So electron capture, it works the exact reverse of positron emission.
It looks like it, doesn't it? Yep. Okay. Oh, we did that. Write the nuclear equation for the decay of phosphorus 32 to sulfur 32 by beta emission. Write the nuclear equation for the decay of phosphorus 32 to sulfur 32 by beta emission. Yeah, so what's the reactant? Phosphorus 32 is going to be a reactant. It's undergoing that decay, and it's turning up, it's ending up as sulfur 32 by beta emission. Looks like there's two reactions here. You should have a part A and a part B. Oh, it's the same thing. Oh, it's the same thing. They just said the same thing twice. They just said the same thing twice. Try it. Try it. See if your try it and see if your subscript and superscripts work out. It should. Phosphorus is element P, right? So hopefully, and sulfur is S. And then they said also beta. What was a beta particle again? It was an electron. It was an electron. All right. So now you have no choice on these numbers. This has to be what. Phosphorus is, 15. Sulfur is 16. Right? You have no choice on those numbers. They have to correspond to what the element symbol is. Phosphorus has 15 protons. It works. Okay. Try to knock out these and we can call it a day. SC. Scandium is SC. No. You'd think I would know by now, right? How many years have I been doing this? Oh, it's 21, yeah. So used to doing radioactive stuff. Scandium is atomic number 21. Thank you. Yeah. They want the reaction for the decay. It decays by emitting a single positron. So you want to write the decay reaction of scandium-41. It's the emission of a positron reaction. So scandium-41 has to be a reactant. So that's how I would start out with that one. Just got to fill in the rest. Cu. I think so. I'm pretty sure. Curium is Cu. You don't have a phone? You can't Google that? No, Cu is copper. Curium, right? Cu is copper. Curium must be Cm. Or Cm. Yeah, because cesium is Cs. Is there a Cm? Curium. If you can beat me. Cr is chromium. It's got to be Cm.
CM's 96.
There it is. I already told you it was Cm. Cm is 96. So just all you have to do is make sure the subscripts and superscripts are the same on both sides. So the superscript has to be what? Has to be a 0, right? Because 27 plus 0, or no, 27 plus 3 is 30, right? This has to be a 3. Because this is 30, this side has to be 30, right? And then the subscripts has to be a 14. That has to be a 2. 13 and 1 is 14. So what plus 12 would give you a 14? So what did you get for 54? What did you get for a subscript? Has to be a what? Has to be a 2 down here. This, and a 3 up on top. So a 2 is HE. All right? Good. So, you okay? So grab your exam. Have a good weekend. Oh, I didn't look it up.
I was like, wow, that's bad. It's like, that's incredibly anti-climactic.
No, someone should have. Someone got the high score. Or this one? Oh yeah, you have to hit it with something, right? So curium is 96, 242. So you have to have 242 there. And they bombarded it with alpha particles, though.
Yeah, I don't get
So
it.
alpha particle.
So is it helium?
So this would have been bombarding it with an electron.
Oh,
They
so,
bombarded it with an alpha particle. That has to be He42.
Oh, so it's not exactly like the exact specific equation.
No, it's yeah. You just have to kind of be careful. They're bombarding, so they're hitting it with alpha particles. So you're right. You got to figure out what he is, but this has to be an alpha particle.
Okay.
Bye, Dr. Smith. Bye, Brad.
Bye, Miss Bailey. You have a good weekend.